In this video, I'm going to sketch the curve given by this function with its derivative and second derivative as given. So I'm going to go through the steps that we discussed in class. So first, we consider the derivatives and find them if we need to, but in this case they're given. Second, I think about the domain of f. This function is undefined when x is equal to 0. The domain of f is minus infinity to 0, union 0 to infinity. Third, I think about symmetry. Now this function is neither even nor odd, so we have no symmetry. And now I think about the intercepts. So when x is equal to 0, f of x is undefined. 0 is not in the domain, so there is no y-intercept. On the other hand, when y is equal to 0, that means that we're going to have 2x plus 1 equal to 0, so that means that x is minus 1. So I have an x-intercept at minus 1, 0. So next, I need to think about asymptotes. So let's discuss first if there are any horizontal asymptotes. So for horizontal asymptotes, I look at the limit as x tends to infinity and the limit as x tends to minus infinity of my function. And my function was 2 times x plus 1 over 3x squared. And we know by what we called the quick trick, that theorem that we talked about in class, that this is equal to the limit as x tends to infinity of 2x over 3x squared, which is the limit as x tends to infinity of 2 over 3x, which is 0. So that tells me right away that y equals 0 is a horizontal asymptote. But I should also examine the limit as x tends to minus infinity of the function. So for the limit as x tends to minus infinity, we can use the same approach, and again that's equal to the limit as x tends to minus infinity of 2 over 3x, which is 0. So as x gets very large, my function is tending to 0, and as x gets very small, my function is also tending to 0. But in any case, y equals 0 is a horizontal asymptote. Now let's discuss vertical asymptotes. Now I'm dealing with a rational function and the denominator is equal to 0 at x equals 0. So that tells me that x equals 0 is a vertical asymptote. But I still need to check the limit as x tends to 0 from the right and the limit as x tends to 0 from the left. First of all, to prove that it's a vertical asymptote, but also to tell me what my graph looks like. So when I'm looking at the limit as x tends to 0 from the right, I do know that this is going to tend to plus or minus infinity, and I just need to determine the sign. Now, on the numerator, as x is tending to 0 from the right, this is going to be positive, and on the denominator, it's also going to be positive. So I know that this limit is positive infinity. For the second limit, the same thing happens. As x tends to 0 from the left, so x is a little bit less than 0, this is going to be positive, but this will also be positive. So even though the x values that I'm considering are negative, I'm squaring them, so that remains positive. So this also tends to positive infinity. Next, we should consider intervals of increase-decrease, and to do that we need to look at the derivative and look for our critical numbers. So recall that this was our derivative. Now f prime x will be 0 when the numerator of this is equal to 0, so that's when x is minus 2. And f prime x would be undefined at x equals 0, but 0 is not in the domain, so that's not a critical number. So our critical number is x equals minus 2. Now let's do a sign diagram for the derivative using the critical number and the vertical asymptote. So I've gone ahead and drawn my sign diagram. I've got my critical number minus 2 on the sign diagram and the vertical asymptote. And this is a sign diagram for the derivative, which I've written up here. So on the rightmost interval, I can check that this derivative is going to be negative. And as I move on to my next interval, it's going to be positive. And on the last interval here, the derivative is going to be negative. So on this interval, my function is then decreasing because the derivative is negative. On this interval, my function is increasing because the derivative is positive. And here the derivative is negative, so it's decreasing. And I should write out my intervals of increase, decrease. F is decreasing on minus infinity to minus 2, union 0 to infinity, and F is increasing on minus 2 to 0. Next, I should consider whether I have any local maxima or minima. But here I can see that I have a local minimum at minus 2 because F is decreasing to the left of minus 2 and it's increasing to the right of minus 2. So that tells me that x equals minus 2 gives a local min, and I should now determine the y value. So I've gone ahead and evaluated my function at x equals minus 2 to get the y value. So that tells me that my local min, which is a point I should put on my graph, is at minus 2 and minus 1/6. So next I need to consider concavity, and to do that I look at the second derivative, and I want to do a sign diagram for the second derivative. And to determine where f prime x is equal to 0, that would be when the numerator is equal to 0. So f prime prime x is 0 when x is minus 3. That's a possible inflection point and a point that I should include on my sign diagram. And as well, I should again include the vertical asymptote x equals 0 on my sign diagram. So I've gone ahead and started the sign diagram. And on the rightmost interval, my second derivative, which I've given here, is positive. So I know it's concave up. The function's concave up on that interval. Moving along to the next interval, the sign doesn't change. It's also positive. The second derivative is positive on that interval. And moving along to the next interval, the sign of the second derivative does change, and it's negative on that interval, so it's concave down. And that also tells me that minus 3 will give me an inflection point because it switches from concave down to concave up at minus 3. So I should list my intervals of concavity. It's concave down on minus infinity to minus 3, and it's concave up on the union of these two intervals. Note that I couldn't include 0 because 0 is not in the domain of the function. As well, I have an inflection point at x equals minus 3. So x equals minus 3 gives an inflection point. And I should figure out the y value by evaluating my function at x equals minus 3. So I've determined that my y value for the inflection point is minus 4 over 27. So my inflection point is minus 3 and minus 4 over 27, which is a point I must include and label on my graph. So next I'm going to use all this information to go ahead and sketch my curve. So here's a sketch of the curve. Note that I've included all important information, like the vertical asymptote, the horizontal asymptote, the intercept, the local minimum, and the inflection point. And you should check that indeed I've made sure that it was increasing on the intervals of increase and decreasing on the intervals of decrease. At my inflection point, I switch from concave down to concave up, etc.